Howdy folks. What we're going to do in this video is we are going to review a subject called special right triangles. Okay, now you probably learned this subject, I'm guessing probably 9th or 10th grade. You may have even learned it in maybe 7th grade or something, and you may not have known why you learned it. But I know why, well, I know one of the reasons why you learned about special right triangles, and that's one of the reasons that I'm going to review it with you, is because we are about to go into the subject that requires you to understand certain characteristics of two special right triangles, okay? And what you can see here is this is a right triangle. And over here, you may say, well, Mr. Ryan, that is not a right triangle. That is true. This is an equilateral triangle. However, what we are going to do is we're going to take this equilateral triangle and we are going to use part of it as a special right triangle. But we can only take one of these cases at a time. So I'm thinking we should go ahead and start over here with this right triangle. Now, before we discuss any of the qualities about this right triangle, the first thing that I want to do is I want to review the Pythagorean theorem. And the Pythagorean theorem is a special formula of sorts. It's not really a formula. I'm sure you think of it as a formula, but what it really is it is a relationship among the lengths of the three sides of any right triangle. And the Pythagorean theorem, is a squared plus b squared is equal to c squared, where a, b, and c are three sides of a right triangle. In particular, A and B are the legs of a right triangle. Those are the shorter sides. And C is the hypotenuse of a right triangle, or the longer side of a right triangle. So if we look at this right triangle over here, we could say that the hypotenuse, the longer side, and remember the hypotenuse is always across from the right angle. And in this case, we're going to say that this hypotenuse, we're going to call that hypotenuse C. And then what we'll do is maybe we'll call this leg down here, the bottom leg, let's call that A, and we'll call the vertical leg here, we'll call that B. It doesn't really matter which one is A and which one is B. You could call this one A, you could call this one B, it doesn't really matter. But the hypotenuse has to be C. So now, here's what we're going to say about this special right triangle. In this particular special right triangle, what's special about it, there's two things that are special about it. The first one is that the hypotenuse is equal to 1. The hypotenuse is automatically 1. That is the first special thing about this right triangle. The second special thing about this right triangle is that the three angles of a triangle have to add up to 180 degrees, right? So if this one down here is 90, then 180 minus 90 leaves 90 more degrees to put in this angle and this angle. And what's special about this triangle is that these two angles are equal. So we're splitting the 90 in half. 90 divided by 2 is 45. So we're going to put a 45-degree angle in here. And then we're going to put a 45-degree angle. This angle over here is a 45-degree angle. And so this is called a 45, 45, 90 right triangle. But it's a special 45, 45, 90 right triangle. It is a 45, 45, 90 right triangle that has a hypotenuse of 1. Now here's the interesting thing that happens. When you have two other angles that are equal, that means that A and B are also equal. They are the same length, okay? In fact, this particular triangle comes from a square. So when you think of a square that has 4 equal sides, right? So this side is equal to this side. All 4 sides are equal. If we were to cut through that square with a diagonal, what that would do is, and then if we get rid of 1/2 across the diagonal, that would create a 45, 45, 90 right triangle. And that's what we're dealing with here. So here's what we're going to say. We're going to say that in this particular case that A is equal to B. So A equals B. And therefore, since A is equal to B, we really can put an A down here and an A up here. Okay? And now what we can do now is we can fill in a couple pieces of information about this triangle using the Pythagorean theorem. So we have our A squared. This is A squared, right? Plus, now B squared. This was B, but because B is equal to A, we just called it A. So instead of writing B squared, we're going to write A squared again. Equals, and then C, that's equal to 1, right? So we're going to say 1 squared. So we have A squared plus A squared is equal to 1 squared. Well, A squared plus A squared, that's equal to 2A squared. So we're going to simplify this using algebra. So we now have 2A squared equals 1 squared. Well, what's 1 times 1? That equals 1. So 2A squared is equal to 1. See, what I'm trying to do here is, I didn't tell you this at the beginning, but I'm trying to find out how long A is. I'm trying to find out the length of these legs here. And now that I have a single variable and a single equation, I can solve for A. So now here, if we look at this, the next thing I have to do is I have to divide by 2. So I'll divide by 2 here, and I'll divide by 2 here. That'll cancel. And I now have A squared is equal to 1/2. And now to solve for A, I need to do the square root of A squared. So if I do the square root of A squared, I have to do the square root of 1/2. Now, when we extract square roots to solve a quadratic, we normally put plus or minus here. But we are not going to put plus or minus, and the reason we're not going to put plus or minus is because we are dealing with the length of a side of a triangle, and lengths are generally always positive. We generally don't deal in negative lengths. Negative lengths have meaning abstractly, but in the case of a physical triangle, the side has to have a positive length. So we're not going to put a plus or minus. We're just going to leave it as positive. So the square root of A squared, that cancels. And we now have A is equal to the square root of 1/2. Now, one of the things that you can do with square roots is you can distribute the radical to the numerator and the denominator. So what we really have now is the square root of 1 over the square root of 2. That's the same thing as the square root of 1/2. Well, what is the square root of 1? Well, the square root of 1, we're looking for a number that multiplied by itself will give us 1. Well, that's 1. 1 times 1 equals 1. So the square root of 1 is 1. And so our answer now is 1 over the square root of 2. But just endure a few moments longer. In algebra, we have this idea that we do not leave radicals in the denominator of a fraction. One of the things that we prefer to do is rationalize the denominator. See, this square root of 2 is an irrational number. We don't like to have irrational numbers in the denominator. Now, in calculus, it's okay to have irrational numbers in the denominator. But in an algebra class, we don't like irrational numbers in the denominator. And so what we want to do is we want to rationalize the denominator. And typically the way we do that is we multiply by a fraction that has the denominator in the numerator and the denominator. So we're going to multiply by, we got square root of 2 here, so we're going to multiply by the square root of 2 over the square root of 2. And so we have a fraction times a fraction, so we're going to multiply straight across. 1 times the square root of 2 is the square root of 2 over the square root of 2 times the square root of 2. Well, that's 2. Because the square root of 2 times the square root of 2 is the square root of 4, and the square root of 4 is positive 2. So this is our final answer. that A, the length of the leg of that triangle, or both of the legs, is equal to the square root of 2 over 2. And this is an extremely important number in math, in a particular area of math. You're not there yet, but you're going to get there within the next week or two. So here's what I'm going to do. I'm going to come over here and I'm going to say that A is equal to the square root of 2 over 2. And then this A over here is also equal to the square root of 2 over 2. And here's what I want to show you, is that this special right triangle, this triangle, this 45, 45, 90 triangle that has a hypotenuse of 1, I'm going to get rid of a lot of this notation here, is a triangle whose hypotenuse is equal to 1, whose height is equal to the square root of 2 over 2, and whose base is equal to the square root of 2 over 2. And you need to store this special right triangle inside of your brain and remember these numbers. Very important, okay? All right, I'm done with that special right triangle. You need to remember this right triangle, and we're going to move on now over to this other special right triangle. Okay, now we're dealing with this. This is an equilateral triangle. It's not a right triangle, not yet. But here's what's interesting about this equilateral triangle. What makes an equilateral triangle an equilateral triangle? Well, it's equilateral, equal lateral, okay, equal lengths. It has 3 sides that are all the same length. This particular equilateral triangle has 3 sides that are all a length of 1. So this length is 1, this length down here is 1, and this length is 1. So it has 3 sides. Now here's the interesting thing. All triangles have a relationship between their side lengths and the measure of the angles that are across from them. And the larger, so we got side with an angle across, side with an angle across, and side with an angle across. I'm not sure if you remember this or not from your middle school geometry or maybe your high school geometry, but the angle measures across from them are proportional to the length of the side. So if the 3 sides of the triangle are equal, then the 3 angles of the triangle are also equal. And since all triangles, the 3 angles add up to 180 degrees, since these 3 angles are going to be equal, we can divide 180 by 3, and that shows us now that the measure of each one of these angles is 60 degrees, because 180 degrees divided by 3 is 60 degrees. So here's what I know. I know that the measure of each angle inside of this triangle, all 3 angles, have a measure of 60 degrees. So I'll put a 60 degrees here, 60 degrees here, and 60 degrees here. All right, the next thing I want to do is this, I don't want it to be an equilateral triangle anymore. It's not useful to me right now as an equilateral triangle. I want a right triangle. So here's what I'm going to do. I am going to split this triangle in half. I'm going to start up here at the top, the vertex of this angle right up here, and I'm going to draw what is called an altitude. An altitude is a line segment that runs from an angle, or the vertex of an angle in a triangle, and it gets drawn down, and it becomes perpendicular to the line, or to the side that is across from it. Now here's the funny thing that's going to happen is when you draw an altitude on an equilateral triangle, it does a few interesting things. First of all, it creates 2 right triangles. Because when we go from here down to here and make a 90-degree angle, we're going to have a 90-degree angle on the right and a 90-degree angle on the left. Now, we only need one of those right triangles. We don't need both of them, and that's okay. The second thing it does is it cuts the angle that it's coming from. It cuts the angle in half perfectly. So when I draw this altitude from this vertex or from this angle down here, that 60-degree angle is going to get cut in half. So it's going to get cut into 30 degrees and 30 degrees. The third thing that it's going to do is when it is an equilateral triangle, this also works for an isosceles triangle, but in this case it's an equilateral, it's going to cut perfectly in half. It's going to cut the side that it's moving down to. It's going to cut it perfectly in half. So this length of 1 is going to get cut in half, and then we're going to have a length that is 1/2 and another length that is 1/2. Okay? So that's what I'm going to go ahead. I'm going to get this right here, and I'm going to draw a straight line from this angle down perpendicular to this side, the opposite side. There we go. And what that did now is I just drew a line or line segment that is at a 90-degree angle. And now this 60-degree angle is not 60 degrees anymore. I mean, this is still 60 degrees, but what I've now created are two 30-degree angles. So that's 30, and this one over here is 30 degrees. And this length of 1 from here to here, I cut it in half, and now I have 1/2 here, and I have 1/2 here. Okay? Now, I only need one of there's two identical, two congruent right triangles, but I only need one of them. So I'm going to erase the left side one. I'm going to use the right side one. Okay, so I'm going to erase here. I don't need this half of the equilateral triangle. I only need this right triangle. This now is the special right triangle that I am interested in. Okay, so now, and here's what I would like to know. I would like to know the lengths of the three sides. Now I have good news. I already know the lengths of two of the sides because one of the sides, the hypotenuse, C, is still one of the sides from back when it was an equilateral triangle. Okay, so I know that the hypotenuse of this triangle is equal to 1. Also, I know that one of the sides, that the shorter side here, is equal to 1/2 because it's half the length of another one of the sides when it was an equilateral triangle. So let's call this one B. There we go. So we have C, we have B, and now we just need A. So really all we're going to try and do here is we're going to try and identify the length of side A in this right triangle. Since we already know two of the side lengths, we can use the Pythagorean theorem very easily and find the length of A. So let's go over to the Pythagorean theorem, and we'll say A squared plus B is 1/2. So we're going to put a 1/2 in here, and it's going to be squared. So that's B squared equals C is 1. So we're going to put a 1 here, squared. Okay? So let's go ahead and calculate this and try and solve for A. Well, 1 squared, we already did that before in this video. 1 times 1 is 1, right? So this is going to be 1. What about 1/2 squared? So that means we have to do 1/2 times 1/2. So 1/2 times 1/2, multiply two fractions. 1 times 1 is 1, and 2 times 2 is 4. So B squared, 1/2 squared, that's 1/4. So I'll put a 1/4 here. And then we'll just bring down the A squared. And so here's what we have now. a squared plus 1/4 is equal to 1. And I know what you're thinking. I know so badly you want to turn this 1/4 into a decimal and do it as a decimal. And I'm telling you, we're not going to do that. If you use the calculator and you did the 1/2 squared as a decimal, put it back as a 1/4. Okay? It's so much better. It's better to understand this as a fraction than as a decimal. So here's what we're going to do. We're going to solve for a squared. And to do that, we have to subtract 1/4 from both sides, right? We've got to subtract 1/4 from both sides. On this side, it's going to cancel. And we're going to just bring down the a squared. So we have a squared equals, right? Now, what is 1 minus 1/4? Now, I know how to do that in my head. I know what the answer is. And some of you may also know the answer to that. But in case you're not sure what 1 minus 1/4 is as a fraction, let's go over here and let's solve it out, okay? Let's move this out of the way. So we've got 1 minus 1/4, right? Well, in order to solve this, we're going to need a common denominator. We have to turn this 1 into a fraction, right? So we got to make it a number over itself, because any number over itself is equal to 1. So I can turn this 1 into 2 over 2, or 3 over 3, 4 over 4, 5 over 5. I can even make it a decimal over a decimal. But what I need is, I need a denominator of 4. So I'm going to make this 1, I'm going to turn it into 4 over 4. So I'm going to have here 4 over 4 minus 1 over 4. Now I have a common denominator, and I can subtract. Now we just subtract the numerators. 4 minus 1, that's 3, over the common denominator of 4, and now our answer is 3/4. Okay, so a squared is equal to 3 over 4. Now, we don't want a squared, we want a. So in order to find the value of a, we got to do the square root on both sides. So we're going to do the square root here, and we're going to do the square root here. Okay? On this side, it's going to cancel the squared, and we're going to have a is equal to the square root of 3/4. But remember what we did in the last problem? We can actually take the square root, and we can give one square root to the numerator and a separate square root to the denominator. So instead of doing the square root of 3/4, it's going to be the square root of 3 over the square root of 4. Well, we're just about done here. We don't even have to rationalize the denominator, because the square root of 4 is a whole number, right? What is the square root of 4? Well, the square root of 4, the number that multiplied by itself gives you 4, is 2. Square root of 4 is 2. So we're going to say a is equal to the square root of 3 over 2. And that is our value. That's our length for a. So a is the square root of 3 over 2. And so here's what you need to understand from this entire video. You remember the other triangle? If you have a 45, 45, 90 triangle that has a hypotenuse of 1, it has leg lengths of square root of 2 over 2 and square root of 2 over 2. You need to know that. Secondly, if you have a right triangle, a special right triangle whose angles are 30, 60, and 90, 30, 60, and 90, and the hypotenuse is equal to 1, then the shorter leg, this is shorter, is going to be equal to 1/2, and the longer leg is going to be equal to the square root of 3 over 2. And that is all I want you to know from this video, okay? So try to go get a piece of paper out after this video is over, get a piece of paper out and draw a 45, 45, 90 triangle and write out the lengths of the sides, hypotenuse of 1, leg lengths of square root of 2 over 2, square root of 2 over 2, and then draw out a 30, 60, 90 right triangle with a hypotenuse of 1, a short leg of 1/2, and a longer leg of square root of 3 over 2. And if you can remember that, you are ready for the next thing we're going to learn.